all. My name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about wavelets and multi-resolution processing. So, what is wavelet and what are the relations to the multi-resolution processing in image processing and color image processing? We will discuss today. So, wavelet transform is used to analyze a signal or image into a different frequency components at a different resolution scales, that is multi-resolution. This allows revealing images, spatial and frequency attributes simultaneously. In addition, features that might be go to underdetected at one resolution may be easy to spot at another. That is, multi-resolution method views condensed versions of the original array to enable global decisions that otherwise would be impeded to the amount of data present. The concept is applicable to image data processing and scaling, that is digitization or acquisition by computers. So generally when we are going to the color image processing, we have to go for the transformation technique. Why we are going for the transformation technique is we have to reduce the noises and we have to resize the image. Okay, so that is the reason we are using here wavelets and multi-resolutions. Okay, suppose we have to compress the image, that will be depend on our resolution of the image. Suppose we have to reduce the noise, we have to use the filters, that will be depending on our wavelet transforms. So here wavelet transform is the major thing here. So the wavelet transform is used to analyze a signal into a different frequency components at different resolution scales, that is multi-resolution, and it is allows revealing images, spatial and frequency attributes simultaneously. In addition, features that might go underdetected one resolution may be easy to spot to another. So when we are going for the multi-resolution, this multi-resolution views concentrate to the version of the original array to enable global decision. So when we are going for the original image, that is a 3x3 matrix, so we have to change the resolutions, so we have to change the values of the matrix. Okay, so that will be enable global decisions that otherwise would be impeded to amount of data present. The concept is applicable to image data processing and scaling. So it is also called digitization or acquisition of a computer. It is a basic step in image compression system. So when you are going for the image compression, first we are going for the input. So it is the input is a noisy image. So input to output, what is the difference of input to output means? Input is a noisy and output is a noiseless. So in between what we are using means we are using transformation techniques or wavelet transforms. So it is a input is a noisy image, we are going to the wavelet transform. So in the wavelet transform, transformation technique is applied. This transformation technique is depend on your noisy of image. So which type of noise is there? Depend on your type of noise, we are using wavelet transform or transformation method. Here estimating the threshold. Estimating means how much noise is there, how much percentage of noise is there, that is the threshold. Suppose I am taking one image, the image is like this or like this. Okay, so threshold means between the x and y axis, how much of percentage of noise is occurred, how much of noise is there in the original image. So that is the percentage of noise. Okay, here percentage of noise occurred in the original image, that is the estimating the threshold. After then we are apply soft or hard thresholding. Thresholding means we are using the filter. So which type of filter we are using, that will be depend on your noise. If you know the type of noise, then we know the type of filter we need in that. That is apply the soft or hard thresholding. Next one is a inverse wavelet transform. Okay, it is a inversing of the wavelet. So what is the inverse wavelet transform means? Here which type of transform you are using. Suppose here I am using transformation technique for noisy image. Okay, inverse means this transformation technique is inverting, means I am going for the original image, I am getting the original image. So when I am getting the original image, then we have to do inverse wavelet transform. Wavelet transform where for reducing the noise, inverse wavelet transform is getting the original image. Okay, we are getting back the original image. That is a denoised. Here input is a noisy and output is a denoised image. So what are the image compression techniques? So in the image compression, wavelets and multi-resolution, these are all using for compression of the image. Compression of the image. So input to noisy image, that is the input is a noisy image and output it is a wavelet transform for reducing the noise. Here estimating the threshold means how much percentage of noise is occurred. Suppose I have 70 to 80 or 90% of noise is there. So what is the use? The image is nothing, we can't use. Okay, if you are removing the noise also, the image is not identifying image. Why? Because the noise is very high. So depends on your percentage of noise, then we have to use is the filters are possible or not for that noise. Okay, next here apply the filters, that is a soft or hard thresholding. Next inverse wavelet transform means we are getting original back of the input image, that is a inverse wavelet transform. Denoised image means noiseless image, it is a noiseless image. So multi-resolution analysis, it is the representation of a signal, that is of image, in more than one resolution. So when we are going for the multi-resolution analysis, refers to breaking up a signal into a components which produce the original signal exactly when added back together. To be useful for data analysis, how the signal is decomposed is important. So when we are going for the multi-resolution, so in the multi-resolution analysis, multi-resolution analysis means how much percentage of noise is there. So we are getting the thresholding levels, that is a representation of a signal, that is of an image in more than one resolution per scale. So multi-resolution analysis refers to breaking up a signal into a components which produce the original signal exactly when added back together. To be useful for data analysis, how the signal is decomposed is important. So decomposed means I am getting back the output image without noise. So wavelet transform is used to analyze a signal into a different frequency components at a different resolution scales, that is a multi-resolution. It allows revealing images, spatial and frequency attributes simultaneously. In addition, features that might be go undetected at one resolution may be easy to spot at another. So when you are going for the spatial and frequency, spatial means it will be depending on our pixels, frequency means it will be depending on frequency levels. Okay, so every wavelet transform or any multi resolutions are we are dividing into a spatial and a frequency levels. Okay, in addition, features that might be undetected of one resolution may be easy to spot at another. So it is the analyzing of a signal means image into a different frequency components at a different resolution scales, that is called multi-resolution. So it depends on your frequency levels, the multi-resolution value will be occurred. The continuous wavelet transform in contrary returns at array one dimension larger than at input data. For a 1D data, we obtain an image that time frequency plane. We can easily see the signal frequencies evaluation during the signal and compare the spectrum with other signal spectrum. Okay, so the images are in the form of 1D or 2D. 1D or 2D. So if the image is 1D, what are the transformation technique we are using? Which transformation is useful? If I am going for the 2D, which transformation is useful? So it is a continuous wavelet transform. It returns array one dimensional larger than input 1D data. We obtain image of the time frequency plane. We can easily see the signal frequencies evaluation during the signal and compare the spectrum with other signals. Okay, here I am talking about only 1D. Okay, 2D we will discuss later. So what about 1D here? So when I am going for the 1D or 2D image. See here, it is a 3-level, one-dimensional discrete wavelet transform. First one is a filter bank representation. Second one is a results in frequency domain. So x of n is tends to h of n. It is a level 1 coefficient. H of n equal to I of n. H of n, it is a level 2. I of n is equal to h of n into I of n. It is a level 3. So first level, here only h of n is there. Second level, h of n and I of n are there. Third level, I of n, h of n and I of n. Okay. So it is a level 3 approximation. So in the frequency levels, these 3 levels, how can we divide? So in the level 1, it is a high frequency, that is Fn to Fn by 2. Okay, it is a level 1. Fn by 2 to Fn by 4, it is a level 2. Fn by 4 to Fn by 3, it is a level 3. So 3-level, one-dimensional discrete wavelet transform. Here it is a filter bank representation, and the third one is a figure B, results in frequency domain. So we are dividing as a 3 levels: level 1, level 2, level 3. So level 1 is a coefficients, level 2 is a coefficients, and level 3 are the coefficients with approximation values. In the block diagram of figure B, level 1 is a high frequency, level 2 is a high frequency, level 3 dividing as a low frequency and high frequency. So low frequency are calling as a approximation, high frequency is calling as a coefficients. So is our coefficients is a high frequency. Here co-frequencies are the high frequencies. Here coefficients are the high frequencies. But here approximation is a low frequency. We are dividing as a 2, low frequency and high frequency. So low plus high, low plus high, h of n plus I of n. So it is another figure. Suppose I am taking the input signal, dividing as a low pass and a high pass filter. Okay. So when we are going for the low pass filter, the filter is a low pass like this. High pass means low to high like this. Okay. High to low, low pass, low to high. It is a high pass. Okay. Signals are dividing into the low pass and high pass. Okay. I am going whether it is A and a D. So low pass output value is I am taking A, high pass I am taking as a D. So what is A and D we'll discuss. So there are so many types of wavelets and the multi-resolution processings are there. So here we will discuss in the wavelets image pyramid. In this image pyramid, it is the image pyramid. In this image pyramid, it is the first one is a subband, second one is a Hall transform, and the third one is a multi-resolution analysis. In the second type, series expansion. Third one is a scaling function. Fourth one is a wavelet functions. In that wavelet functions, there are subtypes are there. So wavelet series. Second one is a discrete wavelet transform. Third one is a fast wavelet transform. Fourth one is a wavelet packets. So first one, image pyramid. Second one, in the image pyramid, we have the subband coding, Hall transform, multi-resolution. These are the 3 types. Another multi-resolution is the second one. So series expansion, scaling function, and wavelet function. So in that wavelet function, wavelet series, discrete wavelet transform, Fourier wavelet transform, and wavelet packets. So these are the 4 types. So 4 subtypes are there under wavelet series. So image pyramid, subband coding, Hall transform, multi-resolution analysis, series expansion, scaling function, wavelet series, discrete wavelet series, fast wavelet transform, wavelet packets. These are under wavelets and multi-resolution. So what are the need of this all those things? We are going for the multi-resolution with image compression. So here one example. Here figure these are the functions of first one. Figure A is a Fourier transform. Figure B is the wavelet transform. So Fourier transform and wavelet transforms are there. How we are going as a Fourier transform means this equation we are calling as a Fourier transforms. Second one is a wavelet transform. Okay, it is a wavelet transform. These are the Fourier transforms. Okay, it is the input signal, input signal, input signal. Okay, input signal is a continuous waveform. So continuous is converting to the wavelet transform. Continuous transform is converting to the wavelet transform. So these are the functions of Fourier transform and wavelet transform. So image pyramid. So image pyramid, at each level we have an approximation image and a residual image. The original image, which is at the base of pyramid, and its P approximation form to be approximation of the pyramid. The residual output from the residual pyramid. Approximation and residual pyramids are computed in an iterative fashion. A P plus 1 level pyramid is built by executing the operations in the block diagram of P times. Okay, when I'm going to the image pyramid, okay, it is one type of multi-level or multi-resolution. At each level, we have an approximation image of the residual image. Okay, the original image, which is at the base of the pyramid, and its P approximation form to the approximation of the pyramid. The residual outputs from the residual pyramid. Approximation and residual pyramids are computed in an iterative fashion. A P plus 1 level pyramid is built by executing the operation in the block diagram of the P times. Okay, so it is the image pyramid. It is the shape of image pyramid, which are combination of the levels. Okay, level 0, level 1, level 2, so on, level J. So J levels are there. It is the image pyramid. Already we discussed in the previous how we are going to the levels. Okay, here level 1 high frequency, level 2 high frequency, level 3 high plus low. So like this, one dimensional or three dimensional or two dimensional, the filtering techniques are converting into the levels. So like this, here also we are converting to the levels. Here the width is very high, so I am taking here level J. Somewhat it is reduced. Okay, it is very the width is very less levels are there, less level of width. So it is a 1 by 1, 2 by 2, 4 by 4, n by 2 into n by 2, n into n. So it is a image pyramid. So these are the levels. So increasing to decreasing order. So 1 by 1, 2 by 2, 4, like this we are increasing the order. So when you are increasing, the levels also increasing. 1 by 1, level 0, 2 by 2, level 1, 4 by 4, level 2. So like this, n by n, I am taking as a level J. So like this, when we are increasing the levels, then the size of the pixels, the size of the images also increasing. That is the image pyramid. So during the first iteration, the original 2J into 2J image. Okay, I am taking as here J into J, but here I am taking 2J into 2J. So 2 times of this size of the image pyramid. So the 2J into 2J image is applied as the input image. This produces the level J minus 1 approximates and the level J prediction residual results, 6 prediction of results values. Okay, so when I am taking the 2J into 2J image, what are the levels means? It is a level J minus 1 approximation. For iterations, J equal to J minus 1, J minus 2, so on J minus P plus 1. Okay, suppose here J equal to J minus 1 plus J minus 2 plus J minus 3, so on level 0. So like this, the iteration equal to J minus 1 comma J minus 2, so on J minus P plus 1 up to J minus 1 approximation output is used as the input. Each iteration is composed of 3 sequential steps. First one is compute a reduced resolution approximation of the input. This is done by filtering. The input is downsampling, it is a subsampling, and the filter result by a factor of 2.7. So filter, neighborhood averaging, Gaussian filter. The quality of the generated approximation is a function of the filter selected. So when I am going to the different levels of images, that is a pyramid of the image. So the iteration is composed of the 3 sequential steps. Compute a reduced resolution. It is done by filtering at the input of downsampling or subsampling, and the value is 2.7 when it is going to the subsampling. When I am going to the filter, the neighborhood averaging or Gaussian filter, the quality of the generated approximation is a function of the filter. So another one is a subband filter. In the image pyramid, another one is a subband. So when we are going to the subband, in subband coding, an image is decomposed into a set of band limited components called subbands. Okay, band limited that is called subbands. In subband coding, an image is decomposed into a set of band limited components, that is a subbands. Since the bandwidth of the resultant subband is smaller than that of the original image, the subband can be downsampled without loss of information. So when I am choosing the image with the band limited or bandwidth, the resultant subband is smaller than that of the original image. The subband can be downsampled without loss of information. That is the subband coding. So it is the 1D 2-band subband coding and a decoding system. Okay, it is talking about the 1D and 2D, that is the subband system. So here I am taking 1D 2-band subband coding and a decoding system. Here f of n equal to input wave and h of n and 2, it is a 2, and g of n, it is the analysis of the filter synthesis. Okay, analysis is the input side and synthesis at the output side. Okay, so at the input side we are analyzing the filter, we are analyzing the noise, how much noise is there, we are analyzing. Synthesis means we are applying the filter. If we know the how much of noise, percentage of noise, if we know, then we have to use the filter, then that is called the synthesis. Okay, it is at output side. So h0 of n is the first stage, h1 of n is a reverse side. It is also g of n is a top side, g1 of n is a bottom side. F dash is equal to output. So f of n equal to f dash of n. Input image, output image, noisy, it is a noiseless. So 1D 2-band subband coding and decoding systems are here. So here it is a 2D 4-band subsystem. Here 1D 2-band. Okay, it is 1 band and it is a 2-band. Here 2D 4-band. 2D with 4 band. First band, second, third, and 4 bands. Okay, here f of m comma n is the input, f dash of m equal to output. So h0 of m, h1 of m, 2 rows along with m, it is a rows, h0 of n, h1 of n, h0 of n, h1 of n. Okay, so columns along n, columns, columns, columns. Okay, it here one output is a of m comma n, d of m comma n, dh of m comma n, dd of m comma n. So it is the 2D 4-band subband image coding system. It is there in the subband wavelet transform. Next one is a important thing is a Haar transform. Haar proposed the Haar transform in 1910, more than 70 years before the wavelet theory was born. Actually, Haar transform employs the Haar wavelet filter, but it is expressed in a matrix form. Haar wavelet is the oldest and simplest wavelet basis. Haar wavelet is the oldest wavelet transform. It is only the wavelet basis which holds the properties of orthogonal, antisymmetric, and compactly supported. So what is the use of Haar transform? So it is proposed in 1910, more than 70 years before the wavelet theory was born. Haar transform implies Haar wavelet filter. Okay, we are talking about the wavelet filter, not the multi-resolution, but it is expressed in a matrix form. Okay, everything we are taking in a matrix form, 3 by 3 or n by n matrix. Okay, 108, 98, okay, 65, 128, 127, 56, 32, 80, 90, 76, like this. I am taking 3 by 3 matrix. Okay, so Haar transform implies the wavelet, but it expressed in a matrix form. Haar wavelet is the oldest and simplest wavelet basis. Haar wavelet is the oldest one, and it is only the wavelet basis which holds the properties of orthogonal, antisymmetric, and compactly supported. So when we are going into the Haar wavelet is a discontinuous function, not a continuous, discontinuous function, and resembled in a step function. For a function f, the Wavelet transform, it is a HWT equal to Wavelet transform. Or Wavelet transform, or Wavelet transform, that is the HWT. So for a function f, the Hor Wavelet transform is defined as f equal to input equal to a power l by d power l. Already we know that what are the a's and what are the d, a and d. So a power l by d power l. Here a power l equal to a1 a2 so on an by 2. D power l equal to d1 d2 so on d power dn by 2. Here l is the decomposition level, a is the approximation subband, and d is the detail subband. So am equal to f2m plus f2 minus 1 by root 2. dm equal to f2m minus f2m minus 1 by root 2. For m equal to 1 to 1 2 so on n by 2. For m equal to 1 to so on n by 2. So here am and dm are there. That is a two levels. It is a level 0 and level 1. So when I am going for the two levels, that is the AL and DL, level 0 or level 1. So AM equal to F2M plus 2F2M minus 1 by root 2, F2M minus F2M by minus 1 by root 2. M equal to 1 to so on n by 2, 1 to so on n by 2. It is the Hor-Wavelet transform equation. So I am taking one example here. F equal to F1, F2, F3, F4, F5, F6, F7, F8. Okay. So length is 8. Length 8. So why? Because F1 to F8. Then Hor-Wavelet transform decomposes F into an approximation subband containing the low frequencies and a detailed subband containing the high frequencies. Low equal to A equal to F2 plus F1, comma F4 plus F3, comma F6 plus F5, comma F8 plus F7 by root 2. It is a low level value. When I am going for the high level value, D equal to F2 minus F1, F4 minus F3, F6 minus F5, F8 minus F7 by root 2. So low and high. Why? Because I am taking it is a level 0 and it is a level 1. So when I am going for the two levels, here level 0 equal to a power l, level 1 equal to d power l. Here also level 0 equal to am, level 1 equal to dm. Like this, here also I am combining to the low level and high level. When I am going for the low level, a equal to f1 to f8. Here we know that by root 2. When I am going for the high level, equal to d equal to f2 minus f1, f4 minus f3, f6 minus f5, f8 minus f7 by root 2. Like this. So these levels I am dividing as a low and high levels of the subband. When I am going for the band means only one level. When I am going for the subband means multi levels. Band means level, subband means multi level. So here the pyramid decomposition under the Wavelets transform. Okay, low, high, high, high. Okay, so why I am taking low two levels means high level and low level. So here also low level, two low levels are there. Here only one high level, one low level. Here one low level, one high level. Here high level. So how we are getting means like this, low and high levels are there. Low means L, H. So L, H. What is the equation of L? F2 plus F1, F4 plus F3, F6 plus F5, F8 plus F7 by root 2. Here high level means we are subtracting the each frequencies. F2 minus F1, F4 minus F3, F6 minus F5, F8 minus F7 by root 2, like this. So low, high, 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 high. So like this. So it is a 4x4 matrix. Next I am going for the, so in this it is a one matrix, it is a sub matrix. Why? Because I am going for the subband, submatrix or subband. It is a subband. Why? Because in the 4x4 matrix, in the 4x4, another 4x4 is there. That is a subband. Low, high, low, high, high. Here high, low, high, low, high. Okay. It is a decomposition of level 1, decomposition of level 2. It is a multi subband. multi-subband. So the pyramid decomposition using Haar wavelet transform. To apply Haar wavelet transform on images, we first apply a one level Haar wavelet to each row and secondly to each column of the resulting image of the first operation. The resulted image is decomposed into four subbands LL, HL, LH and HH are the four subbands LL, LH, HL, HH. Four levels. So these four levels, the approximation of the original image with the other subbands containing missing the details. The LL subband output from any stage can be decomposed further. So the figure below shows the result of 1 to 2 level of Haar wavelet transform based on the pyramid decomposition. So here low high, that is a 4 levels are there. So here also decomposition of level 1, decomposition of level 2 is there. In the level 2, 4 by 4, another 4 by 4 also mentioned there. That is a 4 levels. So when I am going for the inverse Haar wavelet transform, that is the IHWT, inverse Haar wavelet transform. The inverse of the Haar wavelet transform is computed in the reverse order as follows: F equal to A1 minus D1 by root 2, A1 plus D1 by root 2, so on A n by 2 minus D n by 2 root 2, A n by 2 plus D n by 2 by root 2. To apply inverse wavelet transform of the image, suppose input is there and output is there. So for input I have applied the Haar wavelet transform. For the output I have to apply inverse Haar wavelet transform. Then when I am applying the inverse, then only I will get the original image. So the inverse of the Haar wavelet transform is computed in reverse order as follows: F equal to A1 minus D1 by root 2, A1 plus D1 by root 2, so on A n by 2 minus D n by 2 by root 2, A n by 2 plus D n by 2 by root 2. So when applying the inverse Haar wavelet transform at the output side, first we apply one level inverse. After then we are going for the 2 level inverse. Okay, the resultant is the image of the first operation. What are the statistical properties of wavelet subbands? So the distribution of the LL subband approximates that of the original image, but all non-LL subbands, means low subbands, have a Laplacian distribution. This remains valid of the all depths. That is a decomposition of the level. Decomposition means inverse wavelet, inverse Haar wavelet transform, okay, at output level. That is the statistical properties of wavelet subband. Okay, these are the examples of histogram of low level subband, high level subband, low high and high high. Okay, so low high low, low high, high high. Okay, level 0, level 1, level 2 and level 3. Okay, for the different levels we can observe here different histogram processes are there. Okay, when we are going for the high, all the waveforms at one side only. Okay, here low and high is there. That is the reason complete waveform is occurred. So starting 0 to ending 250. But here only one side only. Only one side. 0 to 100 nothing is there, and 150 to 200 nothing is there. 100 to 150 are occupied. Here H also there. That is the reason here only some small width is occupied. Here high means somewhat width is occupied. Okay, when I am going for the low, completely low means width is very high, width is somewhat low, here somewhat low, here very low is there. Okay, it is the histogram graphical representation of subbands, that is in the form of low subband, high low subband and low high subband and high subbands. Okay, wavelet transformation in the image processing. Any wavelet based image processing approaches has the following steps: compute the 2D discrete wavelet transform of an image discrete wavelet transform. Okay, that is in the 2D or 1D. Alter the transformation coefficients, that are the subbands. Okay, subbands means LL, HL, LH and HH. Okay, compute the inverse transform. Okay, compute the inverse transform means we are using the transformation for inverse. First one is a transformation input, inverse transformation is for output level, for getting the original input. So denoising of the image. So wavelet transform are used in a wide range of image applications. These include image and video compression and feature detection and recognition, image denoising and face recognition. So these are the four types or four purposes or four applications of wavelet transform in a wide range of image applications. Image and video compression, feature detection recognition, image denoising and face recognition. So most applications benefit from the statistical properties of non-LL subbands, the Laplacian distribution of the wavelet coefficients in these subbands. Okay, so finally the wavelet applications are including numerical analysis, signal analysis, control applications, and the analysis of the adjustment of audio signals, and Fourier transform in only able to retrieve the global frequency component or content of a signal. The time information is lost. Okay, so there are majorly applications, or four applications are there. So first one is a numerical analysis, second one is a signal analysis, and third one control applications and the analysis and adjustment of audio signals, and fourth one is a Fourier transform is only able to retrieve the global frequency content of a signal. The time information is lost. Okay, these are the applications and these are the references for the image processing. So finally, what we discussed today means wavelet transform is used to analyze a signal or image into a different frequency components at different resolution scales. That is the multi-resolution. At the multi-resolution method, the contented version of the original image array is enabled global decision that otherwise would be impeded by the amount of data present. The concept is applicable to image data processing and scanning, that is a digitization or acquisition of a computer. So these are the stages or basic steps of image compression. First one is a input noise image, that is a wavelet transform to reduce the noise, and estimating threshold means estimating the percentage of noise, and apply the soft or hard thresholding means applying the filtering process to remove the noise. Inverse wavelet transform means after remove the noise, getting the original or denoising image, that is a denoised. Okay, if I am taking the input image is a f of x, output is a f dash of x. Both are same, but what is the difference means noise or small disturbances will be removing in this stage. So multi-resolution is representing a signal or more than a one resolution or two resolution or multi-resolution, and wavelet transform is to analyzing the signal into different frequency components, and the continuous wavelet transform is contrary retains by array of one-dimensional 1D and two-dimensional 2D with the time frequencies. So when I am going for the levels of image, level 1, level 2, level 3 frequency levels, and level 1 is a high frequency, level 2 is also high frequency, level 3 is a low frequency and high frequencies. Okay, so the signal or image converting into the two types, low pass filter and high pass filter. So low pass, high to low, and low to high, high. Okay, what are the types of filters or types of wavelets or multi-resolutions for image compression? These are the types of image compression: image pyramid, subband coding, Haar transform, multi-resolution analysis, series expansion, scaling function, wavelet series, discrete wavelet transform, fast wavelet transform, wavelet packets. Okay, it is a waveform for functions of Fourier transform is in figure BA, and figure B is the wavelet transform. First one is a Fourier transform, second one is a wavelet transform. So it is the image pyramid. Image pyramid is a size, reducing the size, low size to high size. 1 by 1, 2 by 2 means increasing the size and decreasing the levels. So level 0, level 1, level 2, so on, level j. It is the image pyramid. Okay, here I am taking the 2j into 2j image pyramid. So what is the iterations equal to? J equal to j minus 1, j minus 2, so on, j minus p plus 1 at j minus 1 approximation levels. Here each iteration is computing a reduced resolution approximation, and it is the second one is it is done by filtering it input downsampling or subsampling, and filter is nothing but here neighborhood averaging or Gaussian filtering. Here another one is a subband, means band means only one level, subband means multi levels are there. So when I am going for the subband means low low, low high, high low, high high levels. These are I am calling as a subbands. Band means only one, low or high, but here subbands are there, means multi levels will be there. So here 1D means 2 subbands are there. When I am going for the 2D means 4 subbands are there. 1, 2, 3, 4 subbands are there. So it is a Haar transform wavelet to reducing the noise. It is a Haar transform equation. AM equal to F2M plus 2M minus 1 by root 2. D equal to F2M minus F2M minus 1 by root 2. So here I am taking length 8 of the Haar wavelet transform with the 2 levels, high level and low level. So low level equal to F2 plus F1, F4 plus F3, F6 plus F5, F8 plus F7 by root 2. High level equal to D equal to F2 minus F1, F4 minus F3, F6 minus F5, F8 minus F7. So these are the 4 by 4 4 subbands are there in the figure A, level 1, in the figure 2, level 2, decomposition. In the subband another 4 subbands are there. In the subband another subband. That is a pyramid of Haar wavelet transform. We are applying the inverse wavelet transform for subbands. Okay, how we are in inverse applying the Haar wavelet transform is the output side. At the output side, we are applying the inverse to getting the original image. That is the inverse Haar wavelet transform. Where we are applying means we are applying to the Haar wavelet transform. So here inverse wavelet transform IHWT equal to F equal to A1 minus D1 by root 2, A1 plus D1 by root 2, so on A n by 2 plus D n by 2 by root 2. So what are the statistical properties of wavelet means? Depends on your level of the image, the statistical properties will be changed. So these are the histogram processing of low level, high level, low high level and high level of histogram processing in image pyramid. And wavelet transform of the 2D wavelet transform are using in the coefficients, and wavelet transform are using in the inverse waves. And what are the applications which they are using in image and video compression and detection of recognition, image denoising and face recognition. These are the applications are wavelet transforms. And another some applications are including numeric analysis, signal analysis, control applications with analysis and adjustment of audio signals, and Fourier transform is only able to retrieve the global frequency content of a signal, that is a time information is lost. Okay, these are the applications of wavelet transform. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.